Have you ever actually wondered how long does it really take to shuffle a deck of cards properly? It's a fun question, but it turns out there's this mathematical speed limit to randomness itself. And today, we're going to uncover the secret property that actually dictates how fast order can just completely dissolve into chaos.
So here's the game plan. We're going to kick things off with that simple shuffling problem. Then we'll get visual and see how randomness spreads in these totally different worlds. After that, we'll figure out how to actually measure that spread, uncover the secret number controlling it all, and finally wrap up with why this stuff matters for everything from, Google search to modern AI.
All right, so let's dive right in with something we've all probably thought about, even if we didn't realize it was actually a pretty deep mathematical puzzle.
Yeah, so how many times should you shuffle a deck of cards to make it truly random? You always hear that number, right? Like 7 shuffles? 10? Well, the real answer isn't just some magic number. It's actually about a process called mixing. Basically, how long does it take for a system to completely forget where it started and just become totally unpredictable?
Okay, so to really get a grip on this idea of mixing, let's try to visualize it. Imagine it's like a random walk on a network, or what a mathematician would call a graph. And as you'll see, the structure of that world, the way it's laid out, dramatically changes how fast randomness can spread.
So let's check out 2 really extreme examples to see what I mean. On the left, we've got something called a path graph. Think of it like a single long street. One way in, one way out. And on the right, that's a complete graph. Now imagine a city where every single building has a direct road to every other building, a total web.
So if you're trying to take a random walk on that path graph, you're pretty much stuck on that line. To get from one end to the other, you have 0 shortcuts. You kind of have to meander back and forth, and it just takes a really long time to explore the whole space and get to that random state.
But now, what about that complete graph? Well, from any point, you have a direct connection to every other point. In just one step, you can literally be anywhere. So randomness, it spreads almost instantly. This world mixes unbelievably fast.
Okay, so we've got this gut feeling now, right? We have fast worlds and slow worlds. But how do we make that precise? How can we actually put a number on the speed of randomness?
Well, we measure this with something called the mixing time. And you can really just think of it as a stopwatch for randomness. It's literally counting the number of steps it takes until the system gets to its most stable, most mixed-up state. That final state has a fancy name, the stationary distribution. But for our deck of cards, it just means a perfect shuffle, where any card has an equal shot of being anywhere in the deck.
And when we applied this to our 2 worlds, the difference is, it's just huge. The path graph mixes incredibly slowly. In fact, the time it takes grows with the square of the number of points. So if you double its length, it actually takes 4 times as long to mix. But the complete graph is basically mixed in about 1 step. After just a single jump, that system is already super close to being perfectly random.
All right, so we can clearly see the effect. Some things mix slow, some mix fast. But what's the cause? What is this hidden property, this sort of mathematical fingerprint of a network that actually dictates the speed?
I mean, that's the key question, right? What makes one graph fast and another one slow? Can we find just one single number in a graph's DNA that tells us its mixing time? And it turns out, the answer is a resounding yes.
Intuitively, the answer is all about connectivity. I mean, it makes sense. Slow mixing graphs, like our long path, have what you'd call bottlenecks. These are these narrow parts of the graph that are just hard to get into and hard to get out of. They end up trapping the random walk and stop randomness from spreading out evenly. The official math term for this idea is conductance.
And this brings us to the big secret, the spectral gap. Okay, stay with me here. Imagine that every network has a unique sound, like a set of musical frequencies. We can find these frequencies, they're called eigenvalues, just by looking at the network structure. Now, the loudest, most dominant frequency is always 1. The spectral gap is simply the distance between that top frequency and the second loudest one. And this gap, this one single number, tells us everything we need to know about the network's bottlenecks.
And this image here shows it perfectly. We can plot all of a network's frequencies, its eigenvalues. You can see there's always one right at the very edge, with a value of 1. All the others are sort of clustered inside. Well, the spectral gap is literally that empty space you see between the edge and the very next point. A bigger gap here means a much, much better connected network.
So here's the crucial rule, the big takeaway.
A small spectral gap, meaning that second eigenvalue is really close to 1, that's a huge red flag. It signals that there are bottlenecks, and it means the mixing time is going to be long. But a large spectral gap, that tells you the network is what we call an expander. It's super well connected, and it's going to have a very, very short mixing time.
Okay, so let's just lay out the entire chain of logic here, step by step. It all starts with the physical structure of the graph, right? That structure is what creates or doesn't create bottlenecks. Then, the size of those bottlenecks is perfectly captured by one number, the spectral gap. And finally, that number is what sets the ultimate speed limit for randomness, the mixing time. See how it all connects?
Okay, so this is all really fascinating theory, right? But you might be wondering, does this super abstract number actually have any impact on our daily lives? And the answer is, absolutely. Let's see how. I mean, this concept is absolutely crucial in so many fields. Take machine learning. Algorithms that need to explore a huge space of possibilities, things like MC-MC methods, they totally rely on fast mixing to get you a reliable answer quickly. And hey, remember Google's original PageRank algorithm, the one that ranked all the websites? That was basically just a giant random walk on the internet, and its speed depended entirely on the web's spectral gap. We even use this idea to design things, building special expander networks with massive spectral gaps to create hyper-efficient communication systems and more.
You know, this quote from the source material just sums it up perfectly. The relationship is so direct and so powerful. The mixing time isn't just kind of related to the spectral gap, it's reciprocal. One goes up, the other goes down. Simple as that.
So, if you take away one thing, let it be this. The spectral gap isn't just some mathematical curiosity. It is a single, incredibly powerful number that tells you how well connected any network is, and it sets the fundamental speed limit on how quickly information can spread and how fast that system can get to a state of true randomness.
And that really makes you wonder, doesn't it? I mean, if one single number can reveal so much about something as fundamental as randomness and connectivity, what other hidden mathematical structures are out there, quietly shaping the digital and physical worlds that we rely on every single day?